amazing things are happening in this classroom, and half of the people are away. They're seduced by lots of little K's and U's and J's and brackets, etc. when you do it the way it's done officially. But you know, if this doesn't knock your socks off, then you know, go out, take a deep breath, take a walk, come back and look at it again. I mean, I went fishing, you know, Feynman tried to explain chicken wire to old men, didn't work. But the result is just totally amazing. So, on the right-hand side, there is the law, you know, comes from late 18th century. It's Newton, it's all other kinds of old people, still dead. This is just an ordinary classical thing. You learn this without any reference to anything quantum mechanical or stochastic or in a temperature bath or any of those many things. It has interpretation in mechanics that if you're just in one dimension, so when you look at values of this field, you can order them by time instance, so you have a temporal dimension, and that the thing is called work, and it tells you, you know, how hard you have to work to get from someplace to someplace. And as you well know, is, you know, if you do it smartly, you minimize your work, and if you do it stupidly, you'll have to go into the valley, over the mountain, around, it'll cost you more. So this is in engineering called cost function. But it has some symmetries which have to do with energy being conserved that eventually make it look more complicated. But if you ever learn harmonic oscillator any form as an oscillating string or a matrix or anything, you know, this is that. And if you ever learn that you might, if you deform something, you might be paying nonlinear cost in deformation that's proportional how deformed the thing is, then you have the whole story here. It's 18th century. And now what one does is one says, I fine grain the time, if this is a original Feynman time path integral. I fine grain it. So this is a high dimensional ordinary integral in ordinary real variables. For each variation of this variable, the cost changes. And if this is done cleverly enough in such a way that there is, you know, a minus sign, extremum, etc., it has a property that if you're away from the easy paths, so-called geodesics or something, then this is very expensive, and e to the minus large number is 0, so they don't contribute much. But the amazing thing is that this now works in space-time, and it works in lots of other contexts which are not space-time, but show up in physics, or show up in financial markets, or show up in, you know, many other contexts. And what they have in common is, well, the law as promulgated in the 19th century was very, let's say, Christo fascist or something. There's only one way you can do the thing, and everything else, we cut your head off. So it was extremely sharp. By the time you learn about probability stochastic processes, you know, this becomes gray. I mean, you can do forbidden things, but it'll cost you. But this law is, you know, really no quantum mechanics. Now, if you insist that you're a condensed matter physicist and you do real stuff and not this nonsense, then what you'll do is you'll say, well, this is a phase, and it costs me Planck unit of work. So there is a granularity of phase space, position, momentum, space, and mechanics. And I have to measure this cost in the units of h bar. And then you stick it also on this side to keep, correct dimensionalities. Then the 20th century physics creeps in. Planck constant shows up. This is the year 1900. And it's not true that he thought of quantum mechanics. What he did is he had an ultraviolet divergence, which you would get in any discretized setting. And to make that divergence go away, he granularized his integral, and he found out that everything fits, black body radiation fits, if h bar has a measured quantity, which we now know to, I forgot, let's say 14 digits. He did not invent quantum mechanics. He just tried to, get rid of an infinity in an integral. That's all. And now, what happens if you accept that you have a classical cost and that you allow to wander every place but at the price, you get exactly the same form of the answer. So if you remember, what we were doing is we said, well, partition function is partition function of J. But if you think about it, I really care only about connected pieces. And that forces me to exponentiate this. And then if you think about it, it might be smart. We do this all the time in thermodynamics and many other places. This J was some kind of fake thing I was worrying, but I actually care about the probability distributions. I care about phi. So let me just change the coordinates. And you have to make sure that it's legal to do this change of coordinates. And this comes from a very trivial place. Legendre was not trying to solve quantum mechanics. He was just playing with partial derivatives. What happens if you have a function that depends on two variables and you have to vary two variables? Then you're forced to go from ordinary derivatives to partial derivatives. Google it. There is a Legendre transform from dummies, which is perfect, the first thing that comes up, or second, better than Wiki. If you don't understand what Legendre transform is, just work through it. It's a change of coordinates. And we got through it by fishing and chicken wires. We showed that expectation value of connected first moment, the field, is obtained by taking this generating function and evaluating it in the background J field. So that's how we did our fishing. And that's what you obtain by taking partial derivatives. So if you take the derivative of this, there is no dependence of variable or set of variables phi. So this gives you 0, and this gives you phi, and that's what it is. And if you take a partial derivative with respect to phi, this gives you 0. This gives you current. And this, by definition, is the first derivative of cross-hatch thing, which you then, if you do it in terms of fishing, you realize that's one particle reducible diagram, but that's not the point. The point is that this is a good variable. So the left-hand side depends only on J. The right-hand side depends only on J, so that's fine. And this thing here is, if you told me only thing I'm allowed to do is split into 2 copies of myself or something, have a cubic vertex in here, then this thing says, if I look at the 3-point vertex in a generating function for these diagrams, this starts, that's why we did semi-classical approximation, the tree approximation. It starts like this, like the law. but then includes all possible corrections. So this is, if I have h bars here, this is called quantum action. If I think of it more generally, it's called effective action. It says that even if the law only allowed me on an elementary level, on the single x level, to split in two, so this law was very simple. It had just a cubic term in it. And the quantum action will have all possible number of external legs, not only the third one. And the difference between the two is that this will be dressed by a cloud of what they call virtual particles, loops. If I do it in Feynman diagrams, I can think of it that way. And this includes everything all at once. Well, this only does the rigorous thing, and it's totally amazing. So, so I spend the month doing partial derivatives in weird ways, etc. But, that's the content of the theory. So if you go to that lonely island, once you have joined a hedge fund, embezzled $1 billion, and you go someplace to enjoy the rest of your life, this is what you want to take with you. And you'll be able to reconstruct many, many things that modern physics now. So this, puts you at the level of 1960s, 1970s. Now, what happens today is kind of more interesting, because when you look at these integrals and look at constraints, you might find interesting topologically confined things going on. So there's much more going on today. So this is what I tried to do last time. I didn't quite finish, but maybe it's better this way. Only thing you have to remember is this. The rest is just working out details and making sure you understand how they work.